This unit, we are focusing on a very interesting aspect of motion, circular motion. Now, in order for us to move in a circle, there has to be a net force pointed towards the center of the circle. If we do not have a net force pointed towards the center of the circle, we won't be able to move in a circle. So, to remember this very special net force, we give it a unique name. We call it the centripetal force. All right, so let's give a definition for the centripetal force. Centripetal force is a net force pointed towards the center of a circle. Now, really, centripetal force is just a fancy name for net force. All of the rules that we had for net force earlier this year will apply to centripetal force. And one of those rules that we should keep in mind is the fact that just like the net force, we will not put centripetal force on a force diagram, right? Forces are made up of things like friction, applied force, tension, gravity, and when we want to find the net force, we would just add them all together and find out what was left over. That's what we call the net force. Now, if that net force is pointed towards the center of a circle and causes us to move in a circle, we'll just call it a centripetal force. Now, centripetal is often confused with centrifugal force. So centrifugal force is a force pointed away from the center of a circle. You may hear people refer to centrifugal force in popular media, mostly because people are somewhat familiar with these things called centrifuges. So that F sound is familiar to them, and so they think that it is the centrifugal force that causes things to move in a circle like a centrifuge does. But in fact, pushing away from the center of a circle will never allow us to move in a circle. So we'll maybe make a little star for that. The centrifugal force does not, we'll underline the not part, cause an object to move in a circle. Only the centripetal force, the one with the P, allows us to do that, the one that's pointed in toward the center of the circle. So in your lab, we derived an equation for centripetal force. We will use F sub c to represent centripetal force, and we found that it equals the mass times the speed squared divided by the radius. And this is really the equation that we're going to try to build this entire unit around. So let's just throw that into a nice red box so that our eye will be drawn back to this equation later. Now, when we move in a circle, there are many assumptions that we have to make, so let's note some of them. We are going to assume that speed stays the same as we move in a circle. We will also assume that the instantaneous speed, now what I mean by instantaneous speed is speed at any one particular moment. That instantaneous speed is tangent to the circle. Now you have to remember that word tangent from math class. Tangent to the circle means that we've got this straight line that only kisses the circle at one point. It does not cross the circle at 2 points, just at the one. That is what we would call a tangent line. So if we were perhaps at this point on our circle, then this vector can represent the instantaneous speed at that particular moment. Now, if our centripetal force is removed, so maybe we were swinging something on the end of a string, all of a sudden that string breaks, that means that our centripetal force is removed. The object will fly away on a path that is tangent to the circle. Without that net force pointed towards the center of the circle, we will no longer move in a circle. Again, that net force is taken away. We know that our speed, actually our velocity, will not change without a net force. So that's why we fly on that path tangent to the circle. Now, if you've noticed, I've tried to use the word speed a lot, and I haven't used the word velocity until that last little bit of the lecture. And there's a reason for this. We can't use the word velocity because direction is associated with the word velocity. And when we move in a circle, the direction is always changing. Because our direction is always changing, and because velocity has a direction associated with it, changing that direction means that we change our velocity. So let's draw a quick picture to get a visual of what I'm talking about. Let's start with what we just drew above. Like maybe we're at this point here at the top of our circle, and we have some velocity when we are at that point on the circle. Now, if we move, so perhaps we now are at this point on the circle, my speed is going to stay the same. So how long my vector is will stay the same, but because these vectors are always tangent to the circle, that direction of the vector has now changed. And I can do that really for the entire circle if I wanted to. So as long as I am keeping those vectors the same length, then I'm accurately showing that my speed is staying the same. But now, I mean, we're almost pointed in the exact opposite direction of where we started, so that direction is clearly changing. If we wanted to, we could connect those vectors to represent the change in our velocity, okay? So by changing the direction, we are changing the velocity, and these little red vectors are representing that change. Now, if you remember back in our unit on acceleration, we know that a change in velocity is an acceleration. So those red vectors that are showing our change in velocity, those could also be called acceleration vectors. Now, it is not the kind of acceleration that we've worked with in the past where we are speeding up or slowing down. This is an acceleration that is just associated with a change in direction. And so because we want to keep those two accelerations separate from one another, we will call the acceleration that causes a change in direction but not a change in speed the centripetal acceleration. Okay, and we actually can come up with an equation for centripetal acceleration as well. If we start with Newton's second law, we know that Newton's second law is acceleration equals net force divided by mass. But since we are going to specifically be deriving centripetal acceleration, I'm going to write in Fc instead of Fnet, since Fc is just a fancy name for Fnet, and then divided by mass. Now, we also have an equation for Fc. We wrote it above. It is mv squared over r. So we could write Newton's second law as AC equals mv squared over r divided by m. And for those of you who are very talented at algebra will notice I've got mass in my numerator, I've got mass in my denominator. That cancels out. And so what we're left with as an equation for the centripetal acceleration is speed squared over r. And this will become in handy for us later, so let's put that in a red box as well. Now, linear and centripetal acceleration are really, really different, but they're both called acceleration, so we often confuse them with one another. What I'd like to do is I would like for us to make a real quick table to show the similarities and differences between what we will call linear acceleration, the stuff that we are used to dealing with, the stuff that's all about speeding up and slowing down, and we are going to compare it to centripetal acceleration, this new one that is only about change in direction. Acceleration. There we go. Okay, so things to know about linear acceleration. Linear acceleration always happens in a straight line. Centripetal acceleration, it occurs when you're moving in a circle. Linear acceleration really deals with speeding up and slowing down. But in centripetal acceleration, our speed stays the same. When we are dealing with linear acceleration, there is no direction change. And centripetal acceleration, well, it's all about direction change. So this little table is showing us the differences between linear and centripetal acceleration, right? Why are we accelerating? Is it because we are changing that speed? It must be because of linear acceleration. Is it because we are changing that direction? That must be centripetal acceleration. Now let's turn the page. I have a few other general notes I'd like for us to make about circular motion, things that kind of get forgot or maybe just aren't thought of very much when we think about circular motion. First thing is the definition of period. Period is the time it takes to repeat a pattern. And we've actually used period before. Oh, I don't think I spelled the word repeat correctly. Repeat a pattern. Now, I mean, if we want to talk about that pattern specifically for circular motion, we're talking about like going around a circle once. If you go around the circle once and you time how long it takes you to go around that circle once, you have now taken the period of that circle. You guys used the period in your lab because in the lab we had to calculate what our speed was, and if you remember we said, okay, speed is going to be how far I go, which is once around the circle, 2 pi r, divided by the time it takes for me to go once around the circle, which is that period. So as long as you have a radius and a period, you should be able to find the speed of an object moving in a circle. And this equation is going to be very, very useful for us, so we'll stick it in a red box. A little bit more vocabulary is the word rotation. So rotation, the meaning of rotation is once around the circle. Right? So one rotation would be once around the circumference. So that would be 2 pi r meters. Now RPM, it's another vocabulary term for us. It's actually shorthand for revolutions per minute or rotations per minute. Whenever you see something that is given to you in RPM, they're trying to describe to you some kind of speed, right? How far you go per some amount of time. That's definitely a speed. So Let's do a little bit of dimensional analysis. If you are moving at 1 RPM, you are going at 1 rotation per 1 minute. I want to know how many meters per second that is. Well, we know that 1 rotation is the same thing as 2 pi r meters, and we know that 1 minute is 60 seconds. So if we look at this dimensional analysis, we can say rotations on the top, rotations on the bottom, minutes on the top, minutes on the bottom. I'm left with meters per second, which is what I want. And when we finish these train tracks, we see that this should be 30 pi. Oh no, the 30 is on the wrong side. Sorry, pi r over 30 meters per second. So we can think of 1 rotation per minute as being the same as pi r over 30 meters per second. That's all the information that I think we need right now. I think we should do some practice problems with horizontal circles. So a truck of mass 1,500 kilograms can go around a flat curve with radius 150 meters at a maximum speed of 32 meters per second. I want to know what the centripetal force is. So let's write out everything we know. We know the mass is 1,500 kilograms. We know that the R is 150 meters, and we know that our speed is going to be 32 meters per second. What is my centripetal force? Well, let's use the equation that we derived in the lab, Fc equals mv squared over r. If we put in 1,500 kilograms as our m, if we put in 32 meters per second as our v, if we put in 150 meters as our r, well, this just looks like a plug and chug problem. Throw it all into your calculator, we find that our centripetal force is 10,240 newtons. For part B, what is the maximum speed the truck could take around a curve of radius 75 meters? So it seems to me that some of the stuff from part A is going to stay the same, and some of the stuff is going to be a little bit different. It appears that we have the same truck, so our mass is still going to be 1,500 kilograms. But now our radius has changed. It is now 75 meters. We no longer know what our V is, but we would imagine that our FC would stay the same, so that's still 10,240 newtons. This looks like another FC equals mv squared over r problem, so we can put in 10,240 newtons equals 1,500 kilograms times our mystery V squared over 75 meters. And there's only one thing we don't know, so once we do the algebra, we can find that our maximum speed around this curve is going to be 22.6 meters per second. Let's do one more exercise before we end for today. Our car travels around a corner of radius 10 meters at a speed of 8 meters per second. Friction keeps the car from sliding. So first thing we want to do is draw a force diagram for the car. So I'm going to try to draw this car with a little bit of perspective. That's my horizontal circle. And now I'm going to try to drive this or draw this car. So we've got a wheel and a wheel. And we're going to try to draw the front of the car. Let's see. Here's our lovely windshield, right? And then here's our driver looking right at us. Maybe he's waving hello. Hello. Let's see, we got headlights on a car. So here's the two headlights. So the way we've drawn this is so that the car is going around this curve, and it just so happens that he is facing straight at us as he goes around this curve. That makes it very easy for us to draw the force diagram. So if we think about the forces acting on this car, we have a force of gravity acting on that car, and it's going to go straight down towards the center of the earth. And there is a normal force on the car pushing it up from the ground. Now these should be the only vertical forces, and since we are not accelerating in up or down, they must balance one another. And then the problem is even nice enough to tell us to say that the force of friction is what keeps the car from sliding as it goes through this turn. So if we look at this force diagram, we really want to identify what force is my unbalanced force that's pointed towards the center of the circle, because that tells me what my centripetal force is. Again, centripetal force never goes on the force diagram. We just identify it on the force diagram. And so if I look at this force diagram, it's very clear that we've got only one force that's pointed towards the center of the circle, and it is this force of friction. So the force of friction is going to be our centripetal force. Okay, so we could write this out as FF equals FC. This is what's going to help us solve part B of this problem, find the coefficient of friction necessary to keep the car from sliding. Now, another way that we could write the force of friction is we could write it as mu times Fn. Another way that we could write the centripetal force is mv squared over r. And this is good because we want to find the coefficient of friction. So hopefully, as long as we can get a number for Fn, the m, the v, and the r, we should be able to find mu. Now, I don't directly have a number for Fn, but I recognize that my Fn is the same as my Fg. So we could say that mu times 9.8 newtons per kilogram times our mass is equal to mv squared over r. Now this is good because now as long as I know the m, I know the v, I know the r, then I'm good to go. Now if I look at my knowns in the problem, I know I've got an r of 10 meters. I know I've got a v of 8 meters per second. But I don't have an m. That's okay. If we look at the left-hand side of the equation and the right-hand side of the equation, we have mass on both in every single term on both sides of the equation. So that means that that m cancels out, and we were never going to need the mass in order to solve this problem, which is pretty excellent. So now what we can do is we can say, all right, mu times 9.8 newtons per kilogram equals, and let's start substituting in these numbers, 8 meters per second squared over a radius of 10 meters. And now the only thing I do not know is that mu, and we can do the algebra to find that mu is equal to 0.65. Well done.